Welcome, everyone. Today, we're going to explore the fascinating world of remote sensing. On this first slide, you'll see the title Remote Sensing Types and Sensor Characteristics. During this presentation, we'll look at the different types of remote sensing and the key features of various sensors. We'll also discuss how these tools help us gather valuable information about the Earth's surface. I'm excited to take you through this journey, so let's get started. Let's start by looking at how sensors are classified based on their source of energy. We have two main types, active sensors and passive sensors. Active sensors generate their own energy, like emitting a signal, and then measuring the response, which allows us to gather data even in low light or cloudy conditions. Passive sensors, on the other hand, rely on detecting natural energy, such as sunlight or thermal radiation emitted by objects. This distinction is crucial, because it influences how and when we can use these sensors for remote sensing applications. Now, moving on to how sensors are categorized based on the range of the electromagnetic spectrum they utilize. We have optical remote sensing, which captures visible and near-infrared light. Think of it as what our eyes see. Then, there's thermal remote sensing, which detects heat energy emitted by objects, giving us information about temperature differences. Microwave remote sensing uses longer wavelengths, allowing us to peer through clouds and even the Earth's surface, which is especially useful in various weather conditions. Overall, these are the two broad classes of sensors, each with unique capabilities and applications, that help us gather vital data from the environment. Understanding these classifications helps us choose the right sensor for the specific remote sensing task at hand, which is a key part of the overall theme of how we collect and analyze spatial information. Let's take a closer look at the different types of remote sensors based on their source of energy. There are actually two broad categories we can consider. First, we have passive sensors. These sensors rely on external sources of energy, like the sun, to collect data. An example of this would be a radiometer, which measures radiation coming from the Earth or other objects, without emitting any energy itself. Then, we have active sensors. These are quite different because they generate their own energy within the system. They send out a beam of energy, like a radar signal, and then measure the fraction of that energy that reflects back from the target. Radar is a classic example of an active sensor. Understanding these two types is fundamental, because they influence how we design and interpret remote sensing systems, especially when we're considering their applications in environmental monitoring, mapping, or resource management. So, whether a sensor is passive or active depends on its energy source, which in turn affects how it collects and processes data. Now, let's take a closer look at the types of remote sensors based on the range of the electromagnetic spectrum. Focusing on optical remote sensing, these devices operate within specific parts of the spectrum, namely the visible, near-infrared, middle-infrared, and short-wave infrared regions. What's important here is that these sensors are sensitive to wavelengths ranging from about 300 nanometers to 3,000 nanometers. That means they can detect a wide array of electromagnetic radiation within this range, which is crucial for various applications. Most remote sensors you encounter, including the IRSP6 LISS IV sensor, fall into this optical range. They record electromagnetic radiation within these wavelengths, allowing us to capture detailed information about the Earth's surface. Understanding these spectral ranges helps us grasp how different sensors are designed to capture specific types of data, which ultimately supports our ability to analyze and interpret diverse environmental and geographic phenomena. Let's talk about remote sensors based on the range of the electromagnetic spectrum, starting with thermal remote sensing. These sensors operate in specific thermal wavelength ranges, mainly between 3,000 nanometers and 5,000 nanometers, and then again from 8,000 to 14,000 nanometers. In the range of 3,000 to 5,000 nanometers, these sensors are particularly useful for detecting high-temperature phenomena, like forest fires. They can pick up the intense heat signatures emitted during such events. On the other hand, the 8,000 to 14,000 nanometers range is better suited for observing general Earth features that have lower temperatures. This makes thermal remote sensing quite versatile, especially for applications like fire detection and monitoring thermal pollution. For example, the last 5 bands of the Aster sensor and band 6 of Landsat ETM Plus operate within this thermal range, enabling us to monitor temperature variations effectively. So, understanding these thermal ranges helps us appreciate how remote sensing can be used to detect and analyze temperature-related phenomena across different environments. Let's take a closer look at remote sensors, specifically those based on the range of the electromagnetic spectrum. One important type is microwave remote sensing. These sensors detect backscattered microwaves, which fall within a wavelength range of about 1 millimeter to 1 meter. Now, most microwave sensors are classified as active sensors. That means they have their own built-in sources of energy, unlike passive sensors that rely on natural energy like sunlight. An example of an active microwave sensor is RADARSAT. What makes microwave sensors particularly valuable is their advantage over other types, namely, their ability to operate independently of weather conditions and solar radiation. That means they can provide reliable data regardless of whether it's cloudy, foggy, or nighttime. This robustness makes microwave remote sensing a powerful tool in various applications, especially when consistent data collection is crucial. Overall, understanding the range and capabilities of microwave sensors helps us appreciate how they fit into the broader field of remote sensing and how they enhance our ability to observe and analyze the Earth's surface under diverse conditions. Let's now turn our attention to sensor materials, which are fundamental to the performance of any sensor system. The choice of materials directly impacts sensitivity, durability, and overall effectiveness. Moving on, we have sensor systems themselves. These are the complete setups that include sensors, signal processing units, and communication modules working together to collect and interpret data. Next, we consider resolution, a critical aspect that determines how precisely a sensor can detect changes or details in the environment. Higher resolution means more detailed information, which is essential for accurate analysis. Now, focusing on remote sensors, let's discuss some key characteristics. Remote sensors are fascinating because they can collect data from a distance without physical contact. This makes them ideal for monitoring large or inaccessible areas, like forests, oceans, or even space. Their characteristics include the ability to cover vast areas quickly, often providing real-time data, and being capable of sensing across different wavelengths, like visible, infrared, or microwave, to gather diverse types of information. Understanding these characteristics helps us appreciate the power and versatility of remote sensors in various applications, from environmental monitoring to defense. Connecting these points to our overall theme, it's clear that advancements in sensor materials and systems, along with high-resolution capabilities, are driving forward many innovative solutions in sensing technology. Let's take a closer look at the types of detectors used in optical and optoelectronic systems. First, we have optical film detectors, which rely on photographic film to capture radiation. Then, we have optoelectronic detectors, which are more advanced and convert incoming radiation into electrical signals. Essentially, the sensor or detector's main role is to transform the energy from the radiation into a form that we can record and analyze. However, it's important to understand that no single sensor material can be sensitive to the entire electromagnetic spectrum. This means that depending on the wavelength range you're working with, different materials are needed. That's why, in detector design, we select specific sensor materials tailored to different wavelength ranges to ensure optimal sensitivity and performance. This diversity in sensor materials allows us to effectively detect and analyze a wide variety of radiation types across the spectrum, which is crucial for many applications in imaging, sensing, and communication. So, understanding these differences helps us better choose the right detectors for our specific needs. Let's take a closer look at sensor materials, starting with optical film detectors. These are typically made using silver bromide grains, which play a crucial role in capturing images. Now, you'll notice that different types of films are used depending on the application. For example, black and white films, true color films, and even infrared false color films. Each of these has specific sensitivities to different parts of the electromagnetic spectrum. Black and white, as well as true color films, are sensitive mainly to the visible band, which ranges roughly from 0.4 to 0.7 micrometers. This means they're optimized for the wavelengths our eyes can see. On the other hand, false color films, those used to capture infrared images, have increased sensitivity, extending up to about 0.9 micrometers. This broader sensitivity range allows for capturing more information beyond visible light, which is especially useful in various remote sensing applications. Understanding these differences is key to selecting the right sensor material for the specific imaging purpose, linking back to our overall theme of how sensor technology enables us to gather diverse and valuable data from the environment. Let's take a closer look at some of the key sensor materials used in optoelectronic detection. First, we have photoemissive detectors, which include devices like photocells and photomultipliers. These detectors rely on alkali metal surface coatings, such as cesium or a silver oxygen cesium composite, to effectively emit electrons when illuminated. This process is crucial because it allows these detectors to convert light directly into an electrical signal. Next, we have photoconductive detectors. These are made from photosensitive semiconductors. What's interesting here is that their conductivity increases as the incident photon flux increases, meaning they become more conductive when more light hits them. This property makes them very useful for detecting varying light intensities. Then there are photovoltaic detectors. These operate based on changes in the electrical properties of a semiconductor p-n junction. When light irradiates the junction, it causes a modification, similar to a backward bias current, allowing us to generate a voltage directly from the incident light. Moving on to optoelectronic detectors, we find thermal detectors, which are sensitive to temperature changes caused by incident radiation. They don't rely on electronic or semiconductor properties, but rather on the heat generated by the light. Finally, we have quantum detectors. These are incredibly sensitive to changes in the photon flux itself. They can detect very faint signals because they respond to the quantum nature of light, making them essential for applications requiring high sensitivity. All these materials and types of detectors play vital roles in different applications, depending on the specific needs, whether it's sensitivity, speed, or the nature of the incident radiation. Understanding these distinctions helps us select the right detector for the right task in our overall system design. Now, let's take a look at the non-imaging sensor system. This system includes sounders and altimeters, which are crucial for measuring high-accuracy locations and topographic profiles. They allow us to gather precise elevation and position data, which is vital for many applications. Additionally, we have spectrometers and spectroradiometers, and these instruments are used for measuring high spectral resolution. They help us analyze the Earth's surface and atmosphere in great detail by capturing data across different wavelengths. Moving on to the imaging sensor system, this is where things get visually detailed. These sensors capture images that provide spatial information about the area being observed. The key point here is that imaging sensors complement the non-imaging systems by offering a visual perspective, enabling us to interpret land cover, vegetation, urban development, and more. Together, these systems form a comprehensive approach. Non-imaging sensors give us precise measurements and spectral data, while imaging sensors provide the visual context. This integrated setup enhances our ability to understand and monitor our environment effectively, aligning with our overall goal of comprehensive Earth observation. Now, let's take a look at some of the common types of framing systems used in remote sensing. We have the large format camera, or LFC, which is known for capturing high-resolution images with great detail. Then there's the Hasselblad camera, a well-regarded system famous for its precision and image quality. Finally, the Return Beam Vidicon, or RBV, which was traditionally used for space imaging, offering broad coverage. Moving on to scanning systems, these are crucial for capturing data across different terrains and conditions. The Across-Track Multispectral Scanner, or MSS, scans perpendicular to the flight path, allowing it to gather data across multiple spectral bands in a single pass. Then there's the Along-Track Multispectral Scanner, often called the Push-Broom Scanner, which captures data along the flight path, providing continuous imagery. Lastly, we have side-viewing or side-looking scanners, which are designed to observe areas to the side of the aircraft or satellite, expanding the coverage area. All these systems rely on imaging sensors, which are the core of capturing the data we need. The sensor system's design and technology determine the quality and type of information obtained, making it a fundamental component in remote sensing applications. Understanding these systems helps us appreciate how different sensors and scanners are tailored for specific missions and data needs, tying directly into the broader theme of remote sensing technology. Now let's take a look at the methods of scanning. First, we have the across-track scanning, also known as whisk-broom. In this method, the sensor moves perpendicular to the direction of the area being surveyed, sweeping across it much like a broom. This approach is useful for covering large areas quickly and is often employed in satellite or aerial imaging. Next, there's the along-track scanning, or push-broom method. Here, the sensor moves along the direction of travel, capturing data continuously as it moves forward. Think of it like pushing a broom along a floor, covering the area systematically in a straight line. This method allows for high-resolution data collection and is common in modern satellite sensors. Both of these methods are essential in remote sensing because they determine how we scan and capture the Earth's surface. Choosing the right method depends on the specific application, the resolution required, and the area size. Understanding these techniques helps us appreciate how detailed and versatile our remote sensing capabilities are. Across-track, or what we call a whisk broom, refers to how the scanner observes the Earth in a series of lines. These lines are oriented perpendicular to the direction the sensor platform is moving. Think of it like sweeping across a surface in straight, side-to-side motions. Each of these lines is scanned from one side to the other using a rotating mirror, which we label as A on the diagram. As the platform moves forward over the Earth's surface, each successive scan adds to a larger picture, building up a two-dimensional image of the surface beneath. This method allows us to capture detailed, continuous images by combining many individual lines, giving us a comprehensive view of the area we're studying. It's a clever way to systematically cover large regions while maintaining high resolution and detail. So let's talk about the along-track scanning method, which is also known as push-broom scanning. In this approach, we use a linear array of detectors, which I'll refer to as A, positioned at the focal plane of the image. This image itself, labeled as B, is created by a lens system, which we'll call C. The key idea here is that these detectors are pushed along in the flight track direction. That is, along the path the platform is moving. What's interesting about this method is that it leverages the forward motion of the platform to our advantage. As the platform moves forward, the detectors automatically record successive scan lines, which are essentially cross-sections of the scene below. Over time, this process allows us to build up a complete two-dimensional image of the area we're surveying. This technique is particularly efficient because it continuously captures data along the track, making it ideal for high-resolution imaging over large areas. It's a great example of how we can combine the physical motion of the platform with the detector array to create detailed, comprehensive images, an essential concept in remote sensing and imaging systems. Let's take a look at the advantages of along-track systems. The key idea here is that the array of detectors, combined with the push-broom motion, allows each detector to see and measure the energy from each ground resolution cell for a longer period of time, which we call dwell time. This longer dwell time means that each detector can collect more energy from the target area, which ultimately improves the radiometric resolution. That's how accurately we can measure the energy reflected from the ground. Another important point is that these detectors are usually solid-state microelectronic devices. Because of that, they tend to be smaller, lighter, and require less power compared to other systems. Plus, since they have no moving parts, they are generally more reliable and tend to last longer. All of these factors make along-track systems highly efficient and robust, fitting well into our overall goal of achieving high-quality, reliable remote sensing data. Now, let's talk about resolution, which is essentially our ability to record and display fine details in images. When we use satellite sensors, they cover larger areas, but this means the level of detail we can see isn't very high. So, while satellites are great for getting a broad overview, they don't capture the smaller, more specific features very well. On the other hand, if we fly onboard an airplane, it allows us to focus on much finer details. For example, we can see individual buildings and smaller features on the ground. This higher level of resolution is ideal when detailed, specific information is needed. So the key takeaway here is that the choice of sensor depends on the resolution required for the task. Satellites give us a wide view but less detail, while aircraft-based imaging provides much finer, more detailed images of smaller areas. This balance between area coverage and detail is a crucial aspect of remote sensing technology. Now, let's take a closer look at the different types of resolution that are essential in remote sensing. First, we have spatial resolution, which refers to the smallest detail that a sensor can distinguish on the Earth's surface. Think of it as the level of detail you can see in an image. Higher spatial resolution means finer details. Next is spectral resolution, which deals with the sensor's ability to distinguish between different wavelengths of light. This is crucial because it allows us to identify various materials and features based on their spectral signatures. Moving on, we have radiometric resolution, which describes how well a sensor can detect subtle differences in the intensity of reflected or emitted energy. This impacts the sensor's ability to capture variations in brightness, which can be vital for analyzing surface properties. Lastly, temporal resolution refers to how frequently a sensor revisits the same location. This is important for monitoring changes over time, such as weather patterns, vegetation growth, or urban development. When we consider all these types of resolution together, they help us understand the capabilities and limitations of remote sensing data and how best to utilize it for our specific applications. Let's talk about spatial resolution. This is essentially the sensor's ability to discriminate the smallest object on the ground. In other words, it tells us how detailed the images can be. Think of it as the measure of the smallest area or size on the Earth's surface where the sensor can make an independent measurement. The higher the spatial resolution, the finer the details we can see. This is a crucial concept because it directly impacts how accurately we can analyze and interpret the data from these sensors. Throughout this presentation, understanding spatial resolution helps us evaluate the effectiveness of different sensors for various applications, whether it's mapping, environmental monitoring, or urban planning. Now, let's talk about spatial resolution, which is a crucial aspect of satellite imagery. High spatial resolution typically ranges from about 0.6 to 4 meters, meaning each pixel in the image covers a very small area on the ground. This allows us to see fine details, which is especially useful for applications like urban planning or detailed environmental monitoring. On the other hand, medium spatial resolution falls between 4 and 30 meters. This level offers a good balance, providing more context than high-resolution images, but still capturing useful detail for broader analysis, like land use classification or vegetation studies. Then we have low spatial resolution, which ranges from 30 meters to over 1,000 meters per pixel. These images cover large areas and are great for observing large-scale phenomena such as climate patterns or continental changes, but they don't show fine details. Overall, the spatial resolution essentially tells us the pixel size of the satellite images, which directly impacts how much detail we can see on Earth's surface. Choosing the right resolution depends on your specific needs and the scale of the features you're interested in. This concept ties into the overall theme of remote sensing, understanding how different data qualities serve different purposes in Earth observation. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the IKONOS-PAN image, which has a resolution of 1 meter. This means that each pixel in the image represents a 1 meter square on the ground. Such high resolution allows us to see quite a bit of detail, making it extremely useful for a variety of applications, from urban planning to environmental monitoring. When we compare this to lower resolution images, the level of detail here really helps us identify specific features with clarity. This kind of resolution strikes a good balance between capturing detailed information and managing data volume, which is vital for practical use. Overall, the IKONOS image exemplifies how high-resolution satellite imagery enhances our ability to analyze and interpret geographic information accurately. Here, we have an image of a town in Thailand, captured by the LISS IV sensor on ISRO's ResourceSat-1 satellite. What's really interesting about this slide is how it showcases the capability of remote sensing technology to observe and analyze specific regions on Earth from space. The LISS IV sensor is known for its high-resolution imaging, which allows us to see detailed features of the landscape. This image helps us understand not just the geography, but also the land use patterns, urban development, and environmental features of the area. It ties into our overall theme of how satellite technology enhances our ability to monitor and manage our planet more effectively. So, this example from Thailand illustrates the practical application of remote sensing in real-world scenarios. Let's talk about the resolution of the GeoEye-1 imagery. It has a resolution of 0.41 meters, which is roughly half a meter, but for our commercial customers, it's slightly less at 0.5 meters. This means that the ground resolution is sub-meter, allowing us to see objects on the ground that are approximately 16 inches by 16 inches in size. In practical terms, this level of detail is quite powerful because it enables us to identify fairly small objects from space, which plays a crucial role in applications like urban planning, environmental monitoring, and security. So, when we say GeoEye-1 can discern objects around 16 inches across, we're highlighting its ability to provide detailed, actionable imagery that supports a wide range of critical decision-making processes. This is the opposite of scale. The smaller the scale, the less detail is shown. When we talk about scale and spatial resolution, we're referring to how much detail a map or image can display. Spatial resolution specifically means the size of the cell or pixel that represents a particular area on the ground. The higher the resolution of a raster image, the smaller those cells are, which means we can see more fine details. So, in essence, increasing the resolution allows us to get a clearer, more detailed picture of the landscape. This is important because it impacts how accurately we can analyze and interpret spatial data. Now let's take a closer look at scale and spatial resolution. As you can see here, the data in the image on the left has a lower spatial resolution compared to the data on the right. This essentially means that the cell size, or the smallest unit of data, is larger in the left image. Conversely, in the right image, each cell is smaller, giving us more detailed information. Despite these differences in resolution, it's important to note that both images are displayed at the same scale. So, even though the data itself varies in detail, the visual scale remains consistent. This distinction is crucial because it highlights how the level of detail can vary depending on the resolution, but the scale at which we view the data can be maintained. This concept ties back to our overall theme of understanding how data resolution influences interpretation and decision-making in spatial analysis. Let's talk about spectral resolution, which is really about how well a sensor can distinguish between different wavelengths of light. The key idea here is that the finer the spectral resolution, the narrower the wavelength range that each channel or band can detect. This means that sensors with high spectral resolution can pick up very subtle differences in the light reflected or emitted by objects. Now, hyperspectral sensors are a great example of this. They can detect hundreds of these very narrow spectral bands, spanning from visible light through near-infrared and into mid-infrared. This allows us to gather detailed spectral information across a broad part of the electromagnetic spectrum. And why does this matter? Well, with high spectral resolution, we can make fine discriminations between different targets based on their unique spectral responses. This is incredibly useful for applications like mineral identification, vegetation analysis, or even detecting different materials in a complex scene. So, spectral resolution essentially enhances our ability to analyze and interpret the data we collect from sensors, making it a crucial factor in remote sensing technology. Let's talk about radiometric resolution. This is all about how well a sensor can tell apart subtle differences in the reflected or emitted radiation from various objects. Essentially, it determines how finely the sensor can distinguish variations in brightness or energy. Think of it as the sensor's ability to pick up small changes, which is crucial for detailed analysis. Now, the imagery data we work with are represented by digital numbers. These numbers range from 0 up to a certain maximum value, which is 1 less than a power of 2. This maximum value depends on the number of bits used to encode the data. For example, if we use 8 bits, the range of digital numbers goes from 0 to 255. This range directly influences the radiometric resolution. The higher the number of bits, the more subtle differences we can detect in the data. Connecting this to our overall theme, understanding radiometric resolution helps us grasp how detailed and accurate our satellite images can be. It impacts how well we can analyze features, detect changes, or identify specific objects based on their radiation signatures. So, the key takeaway is that the bits used for encoding directly determine the sensor's ability to resolve small differences in energy, enhancing the quality of our imagery data. Let's talk about radiometric resolution. Essentially, each bit in a digital system records an exponent of 2, meaning one bit can represent 2 to the power of 1, which is 2. The key idea here is that the total number of brightness levels we can detect depends on how many bits we use to represent the energy recorded by the sensor. For example, if we have an 8-bit sensor, then we can have 2 to the 8th power, which equals 256 different digital values. These values range from 0 to 255, giving us a pretty detailed scale for brightness. Now, if we only used 4 bits, then we'd have 2 to the 4th power, which equals 16 values, ranging from 0 to 15. So, fewer bits mean fewer brightness levels and less detail in the recorded data. This concept is important because it directly impacts image quality and the ability to distinguish subtle differences in brightness, which is crucial for accurate remote sensing and analysis. The more bits we use, the finer our resolution in terms of brightness levels, and the better our data quality overall. Let's take a closer look at this table, which highlights the relationship between bits, gray levels, and their corresponding range. As you can see, when we use 1 bit, we have 2 gray levels, which cover a range from 0 to 1. Increasing the bits to 2, we get 4 gray levels with a range from 0 to 3. This pattern continues. With 3 bits, there are 8 gray levels, ranging from 0 to 7, and so on. What this table really emphasizes is that the number of bits directly determines the number of gray levels we can represent. For example, with 8 bits, which is quite common in many imaging systems, we get 256 gray levels, spanning from 0 all the way up to 255. This is what we call radiometric resolution, and it's fundamentally tied to the number of bits we allocate for each pixel. The more bits we have, the finer the gradation of gray levels, and thus, the more detailed the image can be. In essence, the number of bits defines the richness of the image in terms of gray scale variation. It's a key factor in image quality because higher radiometric resolution allows us to distinguish subtle differences in brightness, which is crucial for accurate analysis and interpretation. So, understanding this relationship helps us appreciate why increasing the bits improves image detail, but also why it comes with considerations like increased data size and processing requirements. Let's talk about radiometric resolution. This refers to how well our data can record subtle differences in the amount of electromagnetic radiation, or EMR, that is reflected back from the surface. Essentially, it determines how finely we can distinguish variations in reflectance. For example, a sensor with 2 levels of radiometric resolution can only tell if the reflected EMR is high or low, which is quite limited. On the other hand, a sensor with 16 levels can differentiate among many more subtle differences in reflectance, providing a much more detailed picture. This is important because the higher the radiometric resolution, the better our ability to detect and analyze small variations in the landscape. It connects to the overall theme of data quality and how detailed our remote sensing information can be. So, understanding and choosing the right radiometric resolution is key to capturing the most accurate and meaningful data possible. Now, let's talk about temporal resolution. This refers to a satellite's ability to image the exact same area at the same viewing angle at different points in time. Essentially, it's about how frequently a satellite can revisit the same spot on Earth. We call this the revisit period, which is the time it takes for the satellite to complete one full orbit cycle and return to the same location. This frequency of data collection is crucial because it determines how often we can monitor changes over a particular area. But it's important to remember that the actual temporal resolution isn't just about the satellite's orbit. It also depends on several factors like the sensor's capabilities, the width of the swath it can image in a single pass, the overlap between images, and even the latitude of the area being observed. All these elements together influence how often we can get fresh, useful data for a specific location. So, understanding these aspects helps us optimize satellite imagery for various applications, whether it's environmental monitoring, disaster response, or urban planning. Let's talk about why temporal resolution is so important in remote sensing. A persistent cloud cover often limits our clear view of the Earth's surface, which means we can't always get the detailed images we need at any given time. That's why capturing short-lived phenomena, like floods or oil slicks, becomes so crucial. These events happen quickly and can be easily missed if our imaging isn't frequent enough. This leads us to the necessity of multi-temporal comparisons. By comparing images taken at different times, we can better understand changes and patterns that occur over days, weeks, or even months. For example, seeing how a flood progresses or how an oil spill spreads requires consistent, timely imagery. Another key point is that the appearance of features on the Earth's surface can change over time. Things evolve, whether it's vegetation growth, urban development, or natural disasters. Recognizing these changes is only possible when we have a series of images over time, which underscores the importance of high temporal resolution in our imaging systems. In summary, temporal resolution is vital because it allows us to capture fleeting events, monitor ongoing changes, and improve our understanding of dynamic processes on Earth. It really connects to the overall theme of how important timely data is for accurate and meaningful remote sensing analysis.